present here. Today we are going to start the second session of Unit 2. In that, we are going to see the static CMOS. Already we have started, right? We are going to continue that. So static CMOS, which is consist of PMOS as well as NMOS, right? It is consists of both PMOS and NMOS. It has more. This is the one of the best circuit family in digital VLSI. In most of the application, we can find this static CMOS because it is very easy to design. It is very robust. Standard cells are available. So many, and also the noise margin is very high. So much advantages there when compared to other circuit families. So here we have already started with the design of inverter as well as the two input NAND gate we have seen. Today we are going to see the one more that is 3 input NAND gate. How we have to design already we have started. So now I am going to explain you 3 input NAND gate. Okay. So 3 input means A dot B dot C the whole bar. So here we have 3 variables. So 3 variables means totally 6 transistors are required. So 6 transistors out of this, 3 transistors are PMOS and 3 transistors are NMOS. Right. So here I am having multiplication. So multiplication means already I told you multiplication means we have to use the parallel combination of PMOS. Only this thing you have to remember. So parallel combination means 3 variables. So 3 PMOS transistor I have to use. So totally 3 PMOS transistor I have used. The input of first one is A, the input of second one is B, the input of third one is C. So all we have to connect it parallelly, right? And this is connected to supply VDD. And this is my pull up network. Right, this is my pull up network, and pull down network is always a dual network. That means the pull up network is parallel combination means definitely in pull down network it is a series combination, right? So it will follow the duality. So here I have to use the 3 mode transistor, that is all are NMOS. So we should not include the bubble. The input is A, B as well as C. And here it is connected to ground terminal. Ground is nothing but a logic 0. And this is my pull down network. So always in between these two I have to take the output. Right. So here also as we all know that for the NAND gate, if all the 3 inputs are 1 1, that time only you will be getting output equal to 0. Right. NAND operation you know already. So I will I will tell you. See, all the inputs are 1. If all the inputs are 1, all the transistor, NMOS transistor will goes on. Thereby the output path is connected to the ground terminal. So it will become 0. Ground is nothing but the logic 0. Right. Suppose if any one of the inputs, are 1 minute. If any one of the inputs is 0, if A is 0 means what happened? Definitely this will be on, right? And B and C as well as both the transistors are 1 means definitely these two transistors in off position. But due to this transistor, because the input is 0, no, this transistor is on. So due to this transistor, you will be getting output is connected to supply VDD. So now the output will become 1. So if any one of the input is 0, definitely the output is 1. If all the inputs are 1, you will be getting 0. This is the operation of NAND gate. Okay. So I will explain you how to design some other Boolean expression if they have given means how to design. Y equal to AB plus C. If they have given means, see here AB. First you have to take the multiplication. No. So AB, this is one function, this is another function. So first one function I will start. AB is multiplication. So first of all we have to know 3 variables. So 6 transistors are required. Out of that 3 will be PMOS and 3 will be NMOS. Right. So in this, first I will start with the full up network design. Here we have the multiplication, so I have to use the parallel combination of PMOS transistor, right? So this is the input A and this is my input B. So both are parallelly connected. So after that it is added with the C. So we have the addition means we have to use a series combination. First AB are multiplication, so we have used the parallel combination. With this we are going to add with the C. Okay, series combination. Right? So this is formed the pull-up network. And pull down network is complementary form, right? That is a dual network. So here A and B are connected in parallel means here we have to use the series combination. Okay. And then C will be connected in series in the pull up network. So here we have to connect the parallel combination. I will draw it here. You can understand easily. So this is A and this is my B. Both are we have to connect it in series because opposite to pull up network. Okay, and C is connected in series with A and B, but here we have to connect parallel. So this is my parallel combination. So this is connected to ground. So always we have to take the output from the in between pull up and pull down network, right? So this is the way we have to design the any expression they have given means by using static CMOS, or it is sometimes they will ask you to design the other name is complementary CMOS. Both are same. Okay. So next we are going to see the what are all the design consideration while we are designing these static CMOS circuits. Okay. So design consideration is we have many things, that is input delay ordering effect. Next we are going to see the how to convert the symmetrical gate to asymmetrical gate, and then what is skewed gates, and then finally we are going to see P by N ratios. These are the important things we have to consider while we are designing the static CMOS. First, what is meant by input delay ordering effect? See, if you want to make the design work faster means always we have to consider the inner input should be arrived later than the outer input. Why, I will tell you. First of all, we have to know what is inner input and what is meant by outer input. The input A, which is close to the output Y. So this is called my inner input. Okay. If my input B is close to power supply rate, that is ground or supply, then it is called outer input. So when compared to both the input, if inner input arrive later means I will get the my gate will work faster. How? First we are going to see if both the inputs A equal to B equal to 1. Okay, case 1, I will start this. So both the inputs are 1 means what happened? Definitely both the transistor will goes on. If both are on, what is the delay? We have to find it by using RC delay model, right? So if both are on, definitely my output will goes to 0. How it is going to 0 means this capacitor 2C has to discharge through this transistor, and the 6C capacitor will has to discharge through this path, right? Because here this output is connected to 3 transistor, each having a width of 2. So we have 6 capacitors here, but in this terminal we have to consider the only this lower most transistor drain capacitance 2C. For this transistor source capacitance we should not consider. So what is the delay as per the RC delay model is the propagation delay equal to first 2C capacitance has to discharge through the transistor. So 2C multiplied with the resistance contributed by this transistor is nothing but R by 2, because the width is 2. For NMOS, the formula is R by K. Here the width is 2, so it is R by 2. Plus the 6C capacitor has to discharge through 2 transistor, right? So I have to add 2 transistor resistance R by 2 plus R by 2 into 6C. So totally here it is, I am having RC plus here also I'm having 6 RC, totally 7 RC as per the RC delay model. I'm going to consider the another case. In this case, my input A will be arrived later. First B will be arrived, right? Initially my input A is 0, right? First B is arrived. So because of this B arrived, what happened? This 2C capacitance will be first discharged through this transistor. Okay, right? Next A will be changes from 0 to 1. So when input A is changes from 0 to 1, that time already 2C capacitance is discharged. So now we have to consider only the 6C capacitance. So due to that delay, the propagation delay is due to only the 6C capacitance, not the 2C. Because 2C is already discharged, right? So here I have to multiply the 6C with R by 2 plus R by 2. So that I will get the delay of 6RC. So the conclusion here is, see, when the inner input arrive later than the another input, the propagation delay will be reduces. That means the gate is working faster. This is the conclusion. Clear? So with this, I am going to wind up this session. The next session, we are going to start with the other design consideration, that is few more consideration we have to see. Okay, thank you.